What we don't know is how long it's going to keep doing that for at the same rate as it is today. Our models are inadequate for making projections on that, I would say. We need more process-based understanding, and we need to improve the models. And that will feed directly into improved climate projections, but I think that is one of the frontiers of the science field, I think.
Mm-hmm. Mm-hmm. Any other points? No? Yeah, if not, we'll move on to the next speaker. Thank you, Mike. Our next speaker is Dr. Phil, thank you. Thanks for the reminder. Dr. Phil Williamson. Phil, where are you? Oh, you're here. Thank you. Phil works for NERC-UKRI, here, NERC-UKRI, and he's also at the University of East Anglia. Phil has led the planning and implementation of many multi-million programs on science in the UK and also internationally. In particular, I want to mention the ocean acidification, which was particularly big in this country that Phil was heading. He was a lead author in the IPCC, and we'll talk now about marine ecosystems and dependent communities. Thank you.
Thank you very much, Corinne, and thank you actually, Mike, for setting the scene. So some of the aspects I'm talking about will either complement or take forward a little bit further. So first of all, and you've seen now the cover, or what's going to be the cover of the SROC report. You've seen the front cover, but on the right-hand side, we've got the back cover as well, and that shows that it isn't just about ice on the cold parts of the world, it's also about the nice warm tropics, and it isn't just about the seashore, it's from the sea surface to the depth of the ocean, and as we've heard, the ocean covers the whole world, and that blue circle is Corinne's view of the Pacific, and so that there's a little bit of Papua New Guinea, and there's a little bit of North America there. So, okay, we've heard about the heat, the energy going into the ocean, and how the ocean, it's got a rather different role in the climate system, in that the ocean, as far as I'm concerned, actually is the climate system, because that determines everything else, and that is why everyone everywhere gets affected when the ocean changes. And what IPCC wasn't sure about 20 or 30 years ago when we started all these assessments was whether or not the ocean really would change in the same way as the models and projections indicate. But I want to convince you by the observations and the projections that they got it right in the 1990s. Right, so the extra energy, the heat going in, the ocean temperature increases. Now, it doesn't go up by 1 or 2 degrees, except for the ocean surface, but the small temperature changes throughout the ocean that have now been observed, that there wasn't a global warming hiatus in the ocean continued to warm consistently, and the first 20 or 30 pages of the chapter 5 cover these physicochemical changes: temperature increase, mixing in circulation, sea level rise because the volume expands as the heat enters the ocean, deoxygenation as a consequence of circulation change, sea ice cover, we've heard a little bit about that, and then we hear later about the storms and the heat waves and the extreme events. And the point that I'm trying to make is that the whole system changes. When the ocean changes, everything changes. And also not just the temperature, but we've also got the carbon dioxide. Great that it's going into the ocean, but it's actually having then consequences in the ocean acidification. So all those things, all those changes in the ocean affect everything that lives in the ocean. Most of it's microbial, most of it we don't care much about, but we should do, because everything in the ocean has knock-on effects in some way or another, short-term, long-term, to ocean ecosystem services and to people. Now, the red circles, for those who've got good eyesight, so those who look at the report, there's actually some buildings there, and there's 2 little houses there, so that even in the SROC report, we did take account of human communities and the consequences. So at the end of the day, the reason why we care about it is because of us, but because we're changing the whole world, and the whole thing is going on. Okay, but question at the top of the slide, can we actually be sure that, that we have got it right? And for that, then we turn to one of these famous summary for policymakers diagrams in IPCC reports, that policymakers are expected to look at that and then absorb it all and know everything. We've seen 1 or 2 slides a bit like this already, but there's rather a lot of information there, so I'm going to take you through it sort of step by step. But what that is showing We'll go to the top of it. There's different parts of the world along the top in alphabetical order. Arctic, EBUS, it's equatorial boundary system, North Atlantic, just different regions of the world along the top. And then on the left-hand side, temperature, oxygen, ocean pH. This is the evidence for change. Has this system, in the time of the most recent, of the last few decades, is this system, can we attribute that, the changes, and there's inevitably changes there, can we attribute it to climate change being driven by global warming? And if there's lots of black dots there, then the answer is yes, we've got high confidence or medium confidence, and that whether it goes up or down for physics or chemistry, well, okay, it's changing. So that's 20 up, 20 down, 5. Within one region, it can actually go two ways in different parts, because some of these regions are pretty large. So that shows that the physico-chemical system is changing. And then the next level down in that summary graph was the ecosystems. And here we have, work out all of them, upper water column, corals, whatever. There's some blank spaces because some of those don't occur in those parts of the world, or that we don't have sufficient information. But here, the key information is that for most of the changes there are red rather than blue. Those are the ones that have been assessed as being that they're negative changes. There is a little bit of sort of human valuation and perspective there, but those systems are not in the state that they were. They are assessed as having deteriorated, that there's less of them, or they're not functioning in the same way. So that's the ecosystem changes, and then it's no great surprise that if you have the ecosystem changes, then the ecosystem services that those deliver, fisheries, tourism, habitat services. I've lost the top. You don't need to know where in the world, but most of those changes now, 35 out of all those possibilities, are negative things, bad news, things that we don't want to happen. And that's the observed changes up until now. Okay, what about the future? Now, this is the way that the summary for policymakers was constructed. First of all, we looked at the things that have happened up until now. Then we used the models and our understanding and the processes to say, can we project those? It's not a prediction, it is a projection, because there are different scenarios. And the two scenarios that the chapter 5 was based on, and the optimistic RCP 2.6, low emissions, and then the business as usual pessimistic, high emissions, and the two graphs of the world there showing for the open ocean ecosystems, if we keep temperatures down, then on the left-hand side it looks like there's not much change in terms of net primary production. Now, one issue here, it doesn't actually say which species are doing the production, so there can be biodiversity changes hidden amongst that on the left-hand side. If we keep emissions down, net primary production is going to be pretty much the same. If we let emissions rip, then we're on the right-hand side, and that there's potentially this increase in the polar regions of the higher productivity there, but for most of the tropical bands, it's equal area projections. Most of it is the oranges for not so good news in terms of primary production of the ocean. Now, going up the food chains to the creatures of various sizes, zooplankton, that live in the ocean, what does that mean? Interestingly, actually, the effects become magnified as part of this is projection of species changes, but even on the left-hand side now, there's more pattern, there's more variability there. There's also some uncertainty, but on the right-hand side, now we're going into the oranges and reds, and it looks as though, for the projections of our understanding, there'll be less organisms in the ocean of the shrimps, the crustacean, all the other zooplankton, all the other life there. And the things that we really care about are the fish that we scoop out of the ocean. Here, the projections are just for the coastal regions. But again, on the left-hand side, even though the primary production was projected to stay much the same, we've now got these orange colours coming in, tropical and temperate waters, and it's only in the polar regions where we get the extra warmth and productivity. Optimistically, it does depend on the fish actually migrating and surviving and not being overfished. This is potential, catch potential, not saying we will catch those, and sometimes we're not even achieving that because of overfishing. But that looks like, unfortunately, bad news. Therefore, avoid that, stay on the left-hand side as much as possible. Now, there's another way of presenting this information, and it isn't just sort of RCP 2.6 versus 8.5, it's a more graded way of having the impact. And this is on the left-hand side, we have the the global mean temperature, so that might be the scale that you're more used to. On the right-hand side, we have the temperature of sea surface temperature, slightly lower. It isn't the interior of the ocean, it's the sea surface temperature. But this is these are called burning ember diagrams, and for particular ecosystems, we looked at all the information there and said, how do these ecosystems respond to the rising temperatures? And not surprisingly, some are better than others, but this is arranged in a sequence of sensitivity and vulnerability. And over on the far right, warm water corals, they are the most sensitive. And to explain a little bit more, the current conditions of around 1 degree centigrade is bad news, and you will know about coral bleaching and the fact that it takes longer for recovery because of ocean acidification, and the frequency of major bleaching events is coming along faster and faster. So even under present day state, warm water corals, but they're not going to be, if you could hold it right now, they're not going to be in very good condition, unfortunately, in the future. And there's a lag in the system, in the ocean, of 10 or 20 years before we get the full effects. Now, that's the coral system, and if it goes much above what we are now, 1.52 degrees centigrade, there will be major changes of the warm water coral reefs. I mentioned now that they also suffer from storm damage, sea level rise, pollution, and a whole lot of other things. So if we value corals, then we've got to try and keep the temperature limit as low as possible. On the other ecosystems, very quickly, because I realise that I'm coming to the end, that there's 3 here that I've picked out in addition to the corals: seagrass meadows, salt marshes, and mangrove forests. And they have the title of blue carbon ecosystems because they're net accumulators of carbon in the sediment. That it's rooted vegetation, it's coastal zone, and they send the carbon, organic carbon. It's anoxic, it doesn't decompose, it accumulates over time. It has been proposed that and we discussed it within our chapter, to what extent could blue carbon systems be part of the solution? How much sort of carbon, extra carbon, could they be encouraged to take up? One issue is that we've already lost, it's been estimated between 1/2 and 3/4 of these habitats around the world. Could we put them back again? How well would they function? And then the main issue is sort of how rapidly the climate change occurs. Because we've just seen from the burning embers, they're sensitive to climate change, therefore they're only going to thrive and do well if we can keep the temperatures down. But also for sea level rise, that becomes a critical issue. And it is just possible, if there's no barriers to inland migration, if we let everything flood, then sea level rise would potentially have this negative feedback of actually taking up more carbon dioxide, and that if there's enough sediment and the land can flood, these vegetated habitats can do well. But unfortunately, the rate at which climate change is occurring, with the temperature rise as well, we're into this more likely to be in the positive feedback. When those systems are damaged, they might be replaced one by another. But on the whole, that if there's increased storminess, sea level rise that we're going to hear about, if those systems that used to thrive and do well are no longer able to, then they'll actually be part of the problem rather than part of the solution. I think that statement was actually already made by Mike, so I'll just reinforce it. Very high confidence. Everything in this report has got high confidence, very high confidence. Sometimes not very high confidence, but saying that the benefits of ambitious mitigation and effective adaptation highlights the urgency, prioritise timely, coordinated and enduring action. And I think, if you wish to challenge that, you may do so. But I think that was the key message coming out, that there are alternatives, there are choices, and that's what the future is. Thank you very much. Thank you.
Thank you, Phil. If you would like to just stay here a few minutes, we'll have some questions for Phil. So, I mean, on the ecosystem, you haven't talked about adaptation of ecosystems. So there's a glimpse of hope for me that there's more adaptation potential in ecosystems than there is in other aspects of the climate system. And can you say a few words about this, please?
Of using ecosystems for natural adaptation, of instead of building a seawall, plant the mangrove or whatever, as using it as a natural defense. That is possible if you can counteract the climate change. But if you're uncertain and if you've got a high value property, then it's probably it's not good news to build a seawall, but it might be better having the seawall as well behind the sand dune. But for the capacity for these systems to themselves to adapt, clearly they will be moving their ranges in response to the climate change, and then it depends how rapidly the climate change, whether or not the mangrove starts growing where it didn't used to occur before, or whether it gets heat stressed and curls up and dies.
Thank you. There is a question here. Just Michael is coming.
Thank you. It's the message that you're giving that mangrove swamps in particular are absolutely vital to the world, and they should not be converted at an ever-increasing rate into tourist resorts.
Well, and that is one of the message, but yes, the mangroves, all these coastal ecosystems, it's another example of keep it in the ground, and we won't solve the climate change problem by preserving them, but most countries of the world actually have already got strict laws to say that you're not supposed to chop them down and destroy them. It's a matter of governance, of enforcement, or in some places, and within Europe we have wetlands that any offsetting you're supposed to have twice as much as you're taking out, and that if you do value them for their biodiversity and their climate benefits and their fishery benefits and all the rest, clearly keep mangroves as they are. It's a lot longer process to try and recover and restore than it is that the loss, if you churn them up and chop them down, the loss is over a few months or a year or two. The regaining of that carbon that was lost might take 200 years to get back to what you were 6 months beforehand. So that the long, slow process is the restoration and regaining, and it's the same with forestry. For mangroves, they can carry on bedding down and keeping that carbon in the ground, but don't rely on them. The calculations were that, and even a very ambitious restoration program for coastal habitats, between 0.5% or 1% or not quite sure, but of the global total emissions, it's certainly it's a help. Believe in conservation, but don't believe in it as a climate solution. Was our message from the marine side.
Thank you. There was a question there. There will be time for one more question afterwards if there's one.
Thanks for the very clear, if not somewhat depressing, presentation. I was wondering, you gave a very clear description of the blue carbon negative emission technology. I was wondering if you could say anything about your assessment of other more speculative negative emission technologies in regards to the ocean, or whether you didn't make any assessments.
We did make brief. The main sort of instruction for this report was not to consider mitigation, but nevertheless we did have some comments about the potential benefits of green renewable energy, and there's a few paragraphs about ocean fertilization of the open ocean, of ocean liming, of more sort of categories of approaches called geoengineering. On the whole, that there's a whole lot of issues for public acceptability, for governance, for effectiveness, and that they are somewhat speculative, and certainly I would not be, personally, I don't think they're going to work in the way that that we would like to think. Maybe they will, maybe they won't, but they are high risk, and they, on the whole, there is not the political appetite and the policy appetite for those large-scale manipulations of the environment that might be needed to make that happen.
Yeah, there are two questions here in the back, and then the lady here.
Thanks, Philip. Steve Cornelis from WWF. Just your answer to the previous question, not the last one, the one before that. You said, I think, believe it, so in terms of blue carbon, nature-based solutions, believe in it or don't believe in it as a climate solution. Just to clarify, I think it's, we need to cut energy emissions, we need to cut fossil fuels, all that sort of things. My understanding is that these sort of nature solutions are a complement to those. It can't do it by itself, but you need it to as well as the cutting emissions from the energy system.
I agree. Thank you.
There was another point, maybe last one, the lady in the front. Over there.
Thank you. I just saw a film called 2040, I don't know if anyone else has seen it, and it talked about planting seaweeds in the ocean. Did anyone cover that in your report?
There are some paragraphs about planting seaweed. My caution of that, and it does apply to the mangroves as well, quantifying the benefits and making sure that just because you've got productivity, and the IPCC itself has been guilty of this, they've called sequestration equals uptake of carbon dioxide from the atmosphere without defining how long it has to be taken out of circulation. But for if you want to have a benefit, the problem with seaweed, it rots. You know, it doesn't. The plants that I was mentioning have roots in the sediment, and they drive carbon down into the sediment. And if it's undisturbed there, it stays there. With seaweed, it rots. Some of it might go to the seafloor, some of it might go into the open ocean. But in order to quantify it as an accredited benefit, and saying, oh, we've got lots of seaweed, you know, isn't that a good thing? It probably is, but no more than having a field of wheat is sequestration. You know, it is growing, it is taking up carbon dioxide, and then it's giving it up within 6 months or maybe 2 years or 5 years or so. Most of that will be out in the atmosphere, and that applies to most natural solutions that it's carbon in, it's carbon out. Nature is rough and readily in balance. It's not going to really make to go counteract everything that we're doing. So that's why my caution is of calling it solutions unless you put double quotation marks around it.